castle where the digital dreams come alive. CESCG takes place from May 1 to 5, from visualization to the virtual space. Scientific sessions take their place.
Hello, my name is Peter from the Slovak University of Technology in Bratislava, and together with my colleague Adam, we made an AnnotAid AI-driven data annotation tool for histology images. Automatic processing of digital histology images can greatly benefit from the utilization of deep learning methods. Currently available annotation tools often have a low learning curve with difficult or time-consuming annotations methods. Therefore, in this work, we strive to develop a user-friendly annotation tool that utilizes deep learning methods to facilitate the annotation creation process and to support the diagnosis of Nottingham Grading System criteria in breast cancer. Image annotation is finding, exploring, labeling, and describing the areas of interest in image. This process can be divided into two groups, namely manual, where the users can explore and observe while the findings can be recorded to create annotations. The second approach is automated, where some form of assistance is involved in the process of creating the annotations, which can spot errors or assist, resulting in increased efficiency, speed, and quality. We can mention, for example, one-click annotation, scribble annotation, or annotation in the form of bounding boxes or superpixels. There are a number of tools for viewing and annotating histological images. Each of them excels in specific areas, but also has shortcomings. Probably the best known is QPath, which is implemented in Java and provides support for various formats and plugins that extends the annotation process. Another tool is ASAP, which excels in its speed in image analysis. Orbit is a tool that is implemented in Java like QPath, but its main strength is real-time collaboration. And the last one is Citamine, which is a web-based tool that consists of multiple services wrapped in Docker containers. As a result of the analysis, we gained insights into how the tool should work and what their biggest shortcomings are. The following figures show the interface of these tools. To develop a user-friendly annotation tool, we closely collaborated with medical experts from Comenius University in Bratislava. Therefore, our team comprises of domain expert, UX expert, and AI expert. To manage effective communication within the team, we defined the following communication diagram, where the domain expert takes the lead in the specifying requirements and functionalities of the tool. The UX expert is responsible for communicating with the domain expert to gain clarity on the specified requirements, and the AI expert is tasked with analyzing and implementing requirements put forth by the UX expert, and they focus on developing deep learning methods that support the annotation process.
The architecture diagram delineates two main parts, where the implementation of the blue part is the responsibility of UX expert, and the implementation of gray part is the responsibility of AI expert. The main goal of the UX expert is to create an interface for the annotation tool and integrate AI API created by the AI expert. The user can download the annotation tool from the website, which acts as an interface of the Haze release server, which is connected to our GitHub repository to provide the latest versions of the tool. The annotation tool consists of two main parts. The annotation tool itself, which is a cross-platform desktop application developed in Electron, and image server. Next, the annotation tool is connected to the API to store users' data. At the core of the system lies a local image server, which is initiated as a child process of the annotation tool when it is launched and is used for reading images locally. It is developed in Java and utilizes bioformats library. The main part of the AI API is a database with workers, which are responsible for making predictions. The backend is connected to the data store where the uploaded images are stored. Additionally, there is the same image server microservice used to read those images. The AI API was developed using a fast API framework, and the communication between the annotation tool and the AI API is through REST API. The overall architecture consists of three main components, namely fast API, Redis message broker, and salary worker. The prediction flow is as follows. Upon receiving a request, the backend inserts the request into the message queue of the broker. Subsequently, the client receives a unique task ID and uses the polling technique to query the task result. Salary worker picks up and executes this task based on its workload. The results are stored in the Redis database, which allows fast API backend to retrieve them and provide them to the client.
In the first step, wireframes were created to define the layout of various interface elements, and then the high-fidelity prototype was created. Our design process embraced rapid prototyping by directly implementing tool functionalities. The layout of the screen as well as the other settings of the tool can be modified according to the user preferences, and the key parts and functionalities of the tool include support for having open multiple images of various formats at the same time, support for navigating in high resolution images with the ability to zoom, primary control hub with the annotation tools, image properties with the custom list of classes, annotation properties with preview and the specific functions for annotation, and the list of annotations in a tree structure. In order to enable simplified and more efficient annotations, we defined methods for annotating histological images. We divided these methods into two groups, manual and automated. Manual approaches can be defined as those that do not use any form of AI assistance in the process of creating the annotation. In most cases, these forms of annotation must be performed before running the automated annotation methods, and they consist of basic shapes like rectangle, circle, polygon, or point. Automated annotation approaches can be defined as annotations where only minimal user input is required to specify the domain or interaction that is used as input for the AI models. These methods are divided into two types of operations according to the speed of providing the result. In instant methods, a high response rate is expected. Process analysis takes longer, so we need to avoid the feeling of non-functionality. This diagram shows the sequence of process steps where the cutout area along with the user input needs to be sent to the AI API for processing. The status and the result of operations are then polled at specified time interval.
Nucleic model is used for single-click cell segmentation. We obtained the weights from the Nucleic GitHub repository. The prediction outcome is a segmentation map, which is subsequently adjusted using various post-processing techniques aimed at enhancing the segmentation's map quality. And then the segmentation map is converted into the polygon of points, which are then transmitted to the annotation tool. SAM is employed in the annotation tool for interactive segmentation of higher structures. This model facilitates segmentation using bounding boxes, foreground, and background clicks. The model weights are obtained from the Segment Anything GitHub repository. The predicted segmentation mask is subsequently adjusted using various post-processing techniques identical to the nucleic model. Our main use case, which was specified by the domain experts, was to develop deep learning models to assist in evaluation of individual criteria of the Nottingham Grading System. The Nottingham Grading System is a method used for grading cancer, and it involves evaluation of three morphological criteria, namely mitotic count, nuclear pleomorphism, and tubular formation. Each criterion is assigned a score ranging from 1 to 3, resulting a final score ranging from 3 to 9, where the higher the score, the more severe the patient's condition. The first criterion we addressed was the detection of mitosis. Mitosis is a cell that is in the process of division into two cells. The challenge with this criterion is that it is very easy to confuse these cells with so-called hard negative mitosis, which are ordinary cells that are very similar to mitosis. The best results were obtained by using a two-stage model trained on the Medoc++ dataset. The first stage is a alleviate detector and is used to detect candidates for mitosis and hard negative mitosis, which are then classified by efficient NetB4 model. User testing showed us that the detection of hard negative mitosis is redundant and can be removed in the future. One of the limitations of this tool is that we currently can't do evaluation of this criterion because this criterion must be evaluated from the area of 10 high power fields, and currently we cannot send such a large region to the AI API. So we only do detection of smaller regions. Another criterion for the Nottingham Grading System is nuclear pleomorphism. The evaluation of this criterion consists of how different cancer cells are from normal cells. The AI API includes an efficient NetB4 model trained to classify patches of size 256 times 256 pixels into individual ATPS scores. During inference, the input is divided into patches, and a nuclear ATPS score is predicted for each patch. The ultimate score is determined through a majority voting mechanism. We used the Mythos ATPI 2014 dataset for training, and it was the only dataset we could find. We are not satisfied with the results, and it will be necessary to annotate additional data to improve this model. The last criterion is tubular formation. We didn't address this criterion because we couldn't find any public dataset. In the future, we would like to use this annotation tool to create one within APVV project. This annotation tool is under a constant development, and since the submission of the paper, we have implemented active learning. Active learning is a method which enables us to select some portion of the unlabeled data, give it to the annotator to make annotations, and use them to improve the existing model. Currently, active learning is implemented only for mitosis detection. The annotation app has a special section called active learning, where the user can select an image of which predictions he wants to repair. The user can mark the prediction as correct, incorrect, or skip it. Additionally, he can provide a message explaining the reason for his choice. The same predictions are shown to all users, which enables us to decide the final label based on the voted majority. We have already done a testing session with medical experts where they have predictions of 200 mitoses, but the results are still not known because the testing was done very recently.
We perform multiple usability tests with the domain experts. The last one aims to assess the comparative effectiveness of QPath and our AnnotAid tool. We simulated the determination of a criterion for the number of mitoses addressed by 8 given tasks. 4 participants varying in experience levels with each tool and computer skills undertook test tasks in both platforms. Alongside standard metrics like task completion rate or time, confusion, and rage clicks, we gathered qualitative feedback through open questions and structured questionnaires. You can see examples of questions for the system usability scale questionnaire for both tools. The results leaned towards our tool with the grade of A, while the other tool received the grade of C. Another questionnaire was devoted to comparing tools for different questions, where we can see that 83% of respondents prefer our tool more than QPath. Thank you for coming, and if you have any questions, feel free to ask.
Thank you. So we have now space for some questions from audience.
Thank you for the presentation. I have a question about this changing the annotations. So in one of the visualization, it just showed that the user can just reject or accept the annotation. So what about when the bounding box, for instance, is incorrect? So is there an option to move the bounding box, or do you assume that this is like sufficiently good that it doesn't need to be retrained? Or are you interested in just training the classification model? I don't know. So
we implemented the simplest version of this active learning because we only need this type of response from user, if it's correct or not. and it will be our future work maybe to correct the annotations, bounding box or size, or to assign them the different class, for example.
Thanks. And then I have one more question. So if you collect this data, do you check for consistency amongst the annotators? So for instance, that whether somebody maybe is doing the wrong job, right? Like they are not good enough at this. So is there some mechanism to check for some consistency between the different annotators to make sure that the data has high enough quality?
We show the same annotations to all users, and then we decide the final label by using majority voting. And the testing session was done very recently, so we don't know the results yet.
Thanks.
There was one more question here.
I just wanted to ask how you implemented the segment anything model. Is it running locally, or do you call an API?
I'm sorry, I don't understand the question.
I wanted to ask about the segment anything model. Is this running locally on the PC, or do you call an API?
The segment anything model is deployed in our AI API. First, the user must select bounding box where he wants to do predictions. Then we send this region to the AI API, and we calculate embeddings, and these embeddings are then saved. And subsequently, the user can use bounding boxes and foreground, background clicks to make annotations, and everything is running in our server.
Okay, so thank you very much for your talk. Once again.
Swim to the beach where the pixels play.
And I would like to invite Patrick Kozlik as our last speaker for today.
VR, it's a pixel away.